welcome to Learn Extra Live. I'm Katleho and this is Iti. How are you, Iti?
Hello, Katleho.
Are you good?
I'm all right.
Good.
Hello to the viewers out there.
Hello,
Yeah.
guys. So today we are doing maths because it's Monday and by now we are on the grade 11 show. So welcome, grade 11s. What will we be doing today?
We'll be doing revision of grade 11, the whole cross-section of function, up to 10 functions.
Okay, then functions is good. I know they enjoy functions and it's a good section to work through, hey?
Yeah.
Okay, thank you.
We'll see how I make it easy now.
Thank you.
All right.
So, of course, because I mentioned that it's Monday, I hope you guys haven't forgotten already if it's been a long day for you, but we have prizes. We have our Casio calculator as well as the Casio labeler. So, as you guys know already, it goes to the most awesome, most fantastic, most energetic, most everything mindsets on the page. And the page that I'm talking about is our Facebook page, which is facebook.com/learnextra. And our Twitter handle is @learnextra. Make sure, guys, today, functions revision is going to be yours, guys. So work through it. Be patient with yourselves. Also, don't be that patient that you actually fall asleep on the couch, because we don't want that. We want you guys focused and alert. Thank you again to Liberty for bringing us such an awesome, awesome show. Over to you, Iti.
Thank you, Kateo. Yes, we're going to do the whole cross-section of functions. And I want you to look at it as periodic functions versus non-periodic functions. And starting with periodic functions. Periodic functions, by periodic I'm referring to those functions, basically trigonometric functions. Typically the sine x, cos x, and tan x. All right. So we are going to look at what are the defining features. Just a bit of revision. Let's recap a bit here. The defining features of a sine graph, cosine graph, and a tan graph. Let me take a sine graph first. If I had y equal to sine x as a parent graph, if we draw this, I'm not going to go through the whole thing of tabulating the values. I'm just going to draw it right away. I'm sure you know the shape. It starts off by increasing, then decreases until 360. And of course, there is the other half this side, repeating the same form. So you will notice, obviously, you know what is the period from 360 to 0 degrees, minus 360 to 0, up to 360 degrees. And this is our x, and that is our y. Now, two features that you have to remember. You can see that this is actually a waveform which repeats itself after every 360 degrees. And that quantity we call a period, where we say a period for a sine graph is equal to 360 degrees. This means every 360 degrees, the graph repeats its shape, the S shape in this case. So notice that it started off by increasing, then it was 0 there, and it became negative slope there, and 0 again, positive slope there. All right, so at this point, the highest point is called corresponds to 90 degrees. Then it comes back to 180 degrees. Then over there is 270 degrees. You'll remember that that highest point corresponds to a value of y equals to 1. And on the other side, that corresponds to a value of -1. You can actually look at it as the peaks of the mountain and the valleys. That is the highest point and the lowest point. So there is infinite of them, depending on how far we decide to define our interval to go. So how do we find the amplitude? Now, there is the second defining feature, amplitude. The amplitude, we take it as the distance from the neutral line, which is right at 0, up to the highest point. In this case, the best way to look at it is to say the y at the maximum level minus y at the minimum divided by 2. All right? So what is our y maximum? Our y maximum is 1. We subtract minus 1, which is the lowest point. That divided by 2, it will give you 1 as the amplitude of this graph. I prefer to use this expression, note it, because this expression takes care of the graph, of the amplitude when you have translated it up or down. Because many people have looked at the graph and they find that, let me just give you a quick example to make sure we don't get into that trap. If this graph turned at, let's say, 2 there, and this side it's minus 2, the amplitude becomes 2. But then, if you have this graph translated, suddenly you've got a value that will, okay, let's say this is translated to somewhere there. Now, suddenly, if this is 3 units there, and this is minus 1, you have to basically see that this is not symmetrical about the x-axis, and therefore, this becomes a handy formula to work out the amplitude. All right. More than that, what's the other feature that I want to point out there? Yes, we need to, for any graph, we need to define the domain and the range. The range for a sine graph, you're going to write it as y less than 1 but greater than minus 1. That's our range. Our domain, we have to define it as, in this case, in our case here, we chose from minus 360 to 360. Therefore, we write it as x greater than 360 degrees, minus 360 degrees, but less than 360 degrees. We could have chosen a different interval there. So that's the x interval where your graph exists. That's what your domain is. All right. So that was the sine graph. Let's move on quickly to the next one, which is y equal to cos of x. You'll notice that these are the parent graphs that I'm starting with. Later on, I will basically do transformation on these graphs. That means scaling them up or down, or translating them, or yeah. All right, let's see. In this case, you will remember the shape for this one is just like the sine graph, but it starts off by decreasing, then it increases back to a level 1. So I could have continued that on this side up to 360 minus 360. That is 0 degrees there, and that will be 360 degrees. So again, the period for this graph is going to be the same as that of a sine. Over there, that's 270, and that is 90 degrees there. All right, so the minimum value becomes minus 1. Let me just circle that. So the same way we found those, we described those features for the sine graph, it applies to the cosine graph. The period is 360 degrees. You can see this shape started from minus 360. When it got to 0, it started repeating itself until 360 degrees. All right, so that was the period. And then the amplitude is, we still find it the same way. The maximum is 1 over there, and minus 1. If you do it the same way you did with the sine graph, you end up with the same amplitude of 1. And the range and the domain is exactly the same for the sine and the cosine. So what's the difference between the two? The one starts off at 0, decreasing, whereas the other one increases starting from 0. Okay, I'm talking about the slope. All right, So if we move on to the next one, let's just cover, because there are only three basic functions that you have to worry about. So for a tangent graph, so let's go y equals to tan of x. There's a slight difference here. Between, it's got what you call asymptotes. So you will have at 90 degrees and every other odd multiple of 90 degrees. Let's see. Another odd multiple of 90, that is 3 times, is 270 degrees. So every odd multiple will have that asymptote. Minus 90 degrees, so on. All right, that's 180 there. And 0 degrees. So your graph is going to look like that. All right? Down and up. So every odd multiple, as you can see, you've got this graph, repeating itself. So between 90 and 270 is 180 degrees. So that shape repeats itself every 180 degrees. From minus 90 to 90 is 180 degrees again. So the period for this function, is therefore going to be, let's go, the period for a tan function is going to be 180 degrees. So it repeats itself every 180 degrees. All right. So remember I talked about asymptotes. I just want to pick on all the features there. So it's the period. It also has, in addition, asymptote. Infinite of them. I mean, there's an infinite number of them, depending on how far you have defined your interval. Asymptotes at odd multiples of 90 degrees. All right, and do we have an amplitude? No, we do not have an amplitude. This does not have the peak and the valleys. It does go right to the most negative number and the most positive number up there. So you don't have an amplitude in this case. No amplitude, just to emphasize. No amplitude for this one. Okay, so 2 features important there. You've picked them up. Let's move on to, yes, those are the basic functions. Let's move on to a bit of transformation of these functions. We're going to take first a sine graph and do what? Scale it up. And what do I mean by scaling it up? If you take it that this is y equals to that, y equal to 2 sine x, if it started off in your table as, let's say you had that, and that was y equal to sine x, you now scale it up and say every y value you're going to multiply by 2. So in your table, the values that you get over there, you then double them. Let's see what symbol can we use there. Okay, so 2 times here. All right. So what it means, therefore, is that your y values, typically, if you had sine x, if it was previously at an amplitude of 1, that value must be multiplied by 2, and you end up with 2 times 1 equals 2. So you've actually scaled it up in the vertical direction. Okay, and the same would have applied there. If it was minus 1, then it becomes minus 2. All right, so the period is still the same. we still at 90 degrees there, 0 degrees. Over there, it's 180 degrees. Over there, 270 and 360 degrees. Okay, notice that I've now chosen to draw this thing in the interval from 0 to 360 degrees. So this would then be a graph of y equals to 2 sine of x. All right. And Katleho, will we be able to get questions as we go?
No, it's fine. You can just carry on and we'll do the questions at the end.
All right. So let's move on to the next one. That one that I did was a sine graph, taking it from a parent graph, scaling it up by 2. By 2. Scale factor was 2 there. Now I'm taking a cosine graph, and I'm scaling it down by a factor of 2. 0.5 is the same as half. So we've got y equals to half of cosine x. So if I then draw this graph here, it used to be a cosine graph that starts at, let's say, 1 there. And in fact, let me use this, let me keep it dotted there. What's happening to my eraser there? Okay. All right.
Do you want to erase, E.T.?
Yeah,
you can just press the eraser at the top, yeah. Yes, that's it.
There.
And just click on one.
All right.
And then you can erase. No, with the pen.
Oh, with the pen itself.
Oh, okay. Pick it again.
All right.
You
no,
know
it doesn't.
board.
No, it doesn't matter. Look,
Okay.
Kateho, I'll use. Okay. Let me explain it this way. So from 1 unit as the amplitude, this thing is now every value of y, like we did with the cosine graph, is going to be reduced. If it was 1, it's going to now be half of that. Okay. So this used to be 1 unit there. Now it is half of a unit. The amplitude now has been reduced, scaled down to a half. So essentially that's what scaling up and scaling down is about.
Can we go for an ad break?
I think let's go for an ad break, and we can continue from there.
Okay,
more
perfect.
transformation, more transformation.
Okay, awesome. So you guys heard that. We have so much more after the break. So for this break, just relax and we'll be right back, I promise you. Welcome back, guys. We are busy with some mathematics, and for grade 11s, we are doing functions. We're going across the board on functions. So I hope you guys are so ecstatic for that, and you've learned enough already. So we're going to go on to some more. As you know, we are always doing more because this is so that you can learn more and learn extra. Over to you, E.T.
Thank you, Katleho. You know, one thing our viewers must get used to is that when you're dealing with functions, you cannot divorce it from transformation.
Yes, that's it.
Definitely. All right, let's move on and do some more periodic functions before we move on to non-periodic ones. One more transformation that I wanted to attend to is reflection. Here I have it in combination with the scaling as well. So I have that y is equal to minus tan of 2x. All right. And if I were to sketch that, I would have to remember what the parent graph looks like. The parent graph for a tangent goes in that direction with those asymptotes that I pointed out earlier on. All right? But now, you are going to reflect this. The moment you see a minus in front of a function, you know that that function has been reflected about the x-axis. All right. And another tricky thing is the 2x. We're used to tan x. Suddenly, we've got tan 2x. How do we deal with that? This is going to affect our period. It's going to affect our period. I'll show you an expression that will always help you when it comes to a period. All right. And I did say we need to reflect that. Before we reflect it, let's scale it first. Now, what you'll notice is we were scaling in the vertical direction when we multiplied, when you saw a coefficient in front of the ratio itself. Now you've got a coefficient inside the ratio, sort of a coefficient on the variable, the x variable. So how is that one affected? There is an expression that I'm going to write here that you can always use. If your period is 180 degrees, it is going to be equal to 2x at the end, and you're going to have x equals to 90 degrees as your new period. Okay, initially remember we had 180 equal to x. So x was the period. Now, in this case, the period becomes, in fact, let's put it this way. The period will always be the period for the parent function divided by b. Now, b being the coefficient of x. All right. So that would be bx in this case. So that would have been y equals to tan of bx. So you just take the value of b and divide it into the period that you have. So you do the same if it was the sine and the cosine, but you would have to use 360 as the period. All right, so this tells me every 90 degrees, I will have this graph. In fact, let's take it from this point here. All right, so if a period, remember this thing repeated every, all right, that was a 90 and a 270. Now it's going to be half of that, 45 degrees and 135 degrees. At 90 degrees, okay, let's see. So now what you'll have is a graph that would be like that, but this has to be reflected. This has to be reflected on the x-axis, and maybe I should have kept the dots here. Let's keep the dots and use the solid 4. Right, let's see. So this would have been the parent graph, but once you reflect it, it then every y value becomes changes sign, and this thing becomes a graph that goes in that direction. All right, and in this case, that was 90 degrees, so that goes up to minus 45 degrees. Every 90 degrees, you've got that. So from here to there is 90 degrees. Again, at 90, your graph will look like that. All right. I hope that gives a picture of how the coefficient of x affects the period, and how the minus in front of the ratio changes reflects your graph. All right, let's move on to the next one. I think that's good enough there. If we move on to the next one, we take one more. Let's take the third example on trigonometric functions. And this time round, we're going to look at translation, vertical translation. All right. So if we have that y, your function is y equal to sine x plus 3, all it means is that your original function, which was like that, has been shifted. If this was 1 unit there, it will have to be increased by 3 units, and it will end up at 4 units. All right, so if it was 0 here, you add 3 units, you end up at 3 there. All right, and over there, if it was 0, you end up with 3. So you just plot those key points quickly, and you will be able, from -1 now, from -1, if you add 3 units, that's 1, 2. The third unit, if this is 3 here, 2 will be somewhere there. 2. Okay. So this will be the new point corresponding to that. Finally, if you had a 0 here, you're going to take this up to 3 units there. There is the new shape that we are looking for. And this is now the graph translated by 3 units upward. All right, we've drawn it. Sometimes you'll be asked to state the domain and range. In this case, we didn't specify, but we have drawn it up to 360 degrees. 0 degrees to 360. The domain is x from 0 degrees to 360 degrees. And the range, in this case, it's from, notice now, it starts at 2 and ends at 4. The graph does not exist below that level, and it does not exist above that level. Okay, so the range is where y starts at 1 and including, of course. That equal sign means, yeah, it's included, and that should be less than and equal to 4. That would be the range for our function in this case. And let's move to the next one. Yeah, I think we've covered what we need to cover there. Next one, it's another type of translation. That we did a vertical translation. Now I'm looking at a horizontal translation. You will see that I'm going to affect the x because that is the x-axis. So if you have y equals to cos of 90 minus x, what is going to come out is that this determines by how much you have shifted your graph in the horizontal direction. But then again, notice that you've got 90 minus x, which is not the same as x minus 90. So usually the form that comes up is y equal to, let's say, cos of x minus some angle, something like that. All right? In this case, it means therefore that you've got cosine of, if I put it as, let's raise the eraser there. Okay, so if I want to write it as x minus 90 degrees, I will then have to make sure that there is a minus outside that bracket. Okay, so it's like I've got cos of minus an angle. Cos of minus an angle ends up being the same as cos of that angle. So remember, we've got all students take coffee. That is for our ratios. A quick reminder. So if an angle is in the negative direction, you are beginning to measure in the negative direction, that is clockwise. Then in the first quadrant, this is an acute angle in this case. In the fourth quadrant, our cosine is positive. So that angle becomes, our angle in that case, it becomes positive, I mean. All right, so that being the case, all right, I will need more space here. There is a lot of writing here. We said y is equal to cos of x minus 90. And we said it is the same as cos of 90 minus x. All right. So what we had was a cosine graph that looked like that. All right? And you will notice that in front of the cosine, there is no coefficient that is scaling this up or scaling it down. So we still have 1 as our amplitude. And yes, it is symmetrical about the x-axis. And this is because there is nothing added to, after the cosine ratio. Minus 1 there. Right. So now we are going to translate this thing horizontally 90 degrees. So we had a 90 degrees here and a 180 there, 270, and finally it was a 360 degrees. Now we're going to take this graph and shift it horizontally. Now, what you're going to notice is, although it says x minus 90 here, we take this as a movement in there. Excuse me. That's let's get a rubber there. All right. So this is now going to shift in the right direction. So when you see a minus there, it's going to shift to the right. Okay. Rightward shift. Okay. If it was positive, it was going to be a leftward shift. I will have time to explain that sometime, but that's how it is for now. So over here, we're going to shift it to the right, 90 degrees. So in other words, what used to be a peak at 0 degrees here will actually be shifted by 90 degrees, and that will be our new peak. And followed by that will be what used to be 0 here at 90 degrees will be 0 at 180 degrees. You'll see this has been shifted 90 degrees again. So every key feature is then shifted by 90 degrees. Over there by 90 degrees as well. And you're going to end up with a graph. This one is here. You now have a graph that looks like that. So what used to be, if I can just extend it to that side, minus 90 degrees, now corresponds with 0 degrees because we have moved it 90 units. Now, what you'll notice therefore is that cosine of 90 minus x is the same as sine of x. And you'll remember from when we were defining the ratios that indeed complementary ratios say sine 90 minus theta, let's say, is the same as cos of theta. Or cos of 90 minus theta will be the same as sine of theta. And this shape is exactly, it's evidence to exactly what we are saying here. So this is the graph of y equals to cos of x, 90 minus x, but it's also the same as the graph of sine of x. So that's what horizontal shift does to the graph, to the original graph, the dotted graph in this case. All right, so that's just one shift. Let's move to another example.
Iti, before you do another example, must we go for a quick ad break?
Yeah, we can do that.
Okay, let's do that. Yeah. Let's go for a break so that the next question can be started whole, and just so that you guys can also get refreshed, maybe move around, maybe just get revitalized, but be right back. Welcome back, Mindsetters. I hope you did have a little jog around the room just to get your brains revitalized. And also, if you may have some questions, please shoot them through to us just so that E.T. can go through them. But for now, keep your focus on, guys, because this is such important stuff to go through. And this is where you guys can start taking your notes and stuff and start maybe revising, because exams are soon. It seems like they're far, but they are soon. And some of you are going back to school this week as well. So make sure that everything that you have is just up to date, guys, and so is your work. Your work must always be up to date. Over to you, Iti.
Katleho, I now want to wrap up on this periodic functions.
Okay.
But I want to rather give it to them as a challenge question.
Okay,
they can
that
do
would
it
be
at
perfect.
home.
Okay.
I've got a periodic function that's both translated and scaled up and all that. So it says y equals to tan of 2x minus 90, all in bracket, plus 3. Please go and try and draw this graph and see what the shape will be like. All right, so it's testing everything, almost everything. All right, so I want to move on to non-periodic functions. I'm saying draw graphs of the following algebraic functions, starting with a simple one like y equals to 2x squared. All right, you will identify this as a quadratic function. And the graph that you have coming out of this quadratic function is called a parabola. So the graph out of a quadratic function is called a parabola. And that's what I'm asking you to draw. Okay? Notice that this graph, if it was a parent graph, it would have been y equal to x squared. You have a coefficient on the x squared term, and that is a coefficient 2. It's simply scaling this up by 2 units. I mean, a scale factor of 2. So what you will then have, if you look at a parent graph of a parabola, it would have been something like that. You can see the features of a parabola there, symmetry, and a turning point, and the Y-intercept, all that. So what you have done now is, if this was 1, you would have, if it was a parent graph, it would be 1 squared, which is just 1. Okay, so 1 would correspond to 1. If you substitute there, that would have been a point there. Now, if it was 2, that would come out to be 4, or 2 squared. Now, what you're doing with these values of y, is to basically multiply them by 2. So if you multiply this y value of 1 by 2, you're going to end up with a value of 2 somewhere there. Okay, so let's start off with a 0, with a 2 there. And if you multiply that value of 4 by 2, you're going to end up with a value that is 8 somewhere there. And that becomes your graph. That's how you can quickly sketch your graph. All right, so I'm sure some of you, are saying, well, we know how to do that, but let's just move on to a bit of transformation. Here, what we do is, yes, we've scaled it up, and we also translate it. Now, it's a few combinations now. We're going to translate it vertically by adding a 3 or taking away a 3. So let's take it from the parent graph. If this was your parent graph, in this case, let's take it from 2x squared. So if this was a graph of y equals to 2x squared. So all you would have to do in this first case, I'm going to call this y1 and this y2. In the first case, you would have to increase every critical value, every defining feature, you would have to lift it up by 3 units. So let's say you end up somewhere there with your turning point. Okay, so if there was another point here, which was, say, 1 and 2, you're going to end up with that point sitting up there, multiplied by, first of all, it was multiplied by 2, then 3 was added to that. Okay, so that would end up being 5 units. 5 up there. All right, so that's just the first one. That's Y1. This represents Y1. Then you've got Y2, which says subtract from each Y value on the parent graph, on the graph of 2x squared, take away 3 units. And then you're going to end up, let me just use a different pen there. You end up with, if it was 0, now it will be moved, how many units? 3 units down. So you end up at -3. Did I say 2 there? Let's see, yeah. Then you end up with a graph that looks like that. Simply just shifted down 3 units. I did not point out the new value over there, which is going to be 3. Okay, because it was 0 initially, now it is 3 units up. Okay, that's how you would actually translate your quadratic function. Notice that in this case, our line of symmetry, because we don't have the middle terms in this expression, our line of symmetry is still your y-axis. So this is because you've got an expression that says ax squared simply plus b. You don't have the x term. So remember, a quadratic function has got 3 terms. It's a trinomial. So it would have been y equals to ax squared plus bx plus c, but you just don't have this middle term. So let me just represent this one so that you at least relate to these symbols. So in this case, what you then have is just ax squared plus c. The b term is not there. And now, obviously, you're beginning to realize that the x term has a tendency to change the axis of symmetry of your parabola. Okay, so that's what you have seen with these two translations and scaling. We can move to the next one. Let's see. Now, what I have done is I've brought in the b term, the x squared, the x term, which was missing in the other equation. And let's see what that does to this problem. All right, if we take it one more. Right. So if we had our graph, the parent graph, sitting at that point, like that, the graph of y equals to 2x squared. And now we introduce the x term. What is it going to do to this? Now, if you factorize this, let's take the first one and call it f of x equals to that. This one we'll call g of x equals to 2x squared minus 3x. So what will happen here is, remember the features now, very important for any function when you draw the graph. You need to know what are the defining features. For a parabola, yes, we have a turning point. We have the y-intercept, one y-intercept. And we've got a maximum of 2 x-intercepts. You can have 0, you can have 1. So if you have an expression like that, how do you find the y-intercept? For y-intercept, we let our x equal to 0. So in this case, we end up with y equal to 0 anyway. All right, so this graph will have, will still pass at that point, at the origin. What about the x-intercept? If I may just buy space here. For x-intercept, what we do is let our y equal to 0 that tells us that 2x squared plus x will be equal to 0. Now, is the case of factorizing there. Then we say take away, take a common factor of x, then you've got 2x plus 1 there equal to 0. Your x-intercepts will be x equal to 0 and x equals to minus half. All right, so if we have those three important informations, the y-intercept, the x-intercept, and we know the turning point, do we? No, we don't know the turning point. That's another thing we're going to have to determine there. And all right, how do we determine the turning point? So we've got that. How do you determine the turning point? One little formula that you are going to have to use. At the turning point, x, let me call it T, P, x at the turning point will always be minus b over 2 times a. So b and a represent the coefficients of x squared and the coefficient of x. All right. So if you look at b, our b was 1. So we substitute it. All right. Then we divide that by 2. Where we see a, we put 2. So which means our x-intercept, our axis of symmetry is going to be at minus 1 over 4. All right. So now we've got all the important features that we need to show on the graph. And quickly, let's see. I think we're just short of the y at the turning point. So y at the turning point, all we have to do is go and substitute in that equation because we've got x at the turning point. That's 2 into 1 over 4 squared plus x. Was it x or 3x? Let's just quickly check that. It's actually 3x. That was 3x there. I'll just have to correct this quickly. That's a 3 there. And that becomes 3 over 2. The whole picture has changed. And if I can run quickly there, that's 2 times a. Then the b was 3. Yes, the b was 3. And the a was b over 2. The 3 is here. And that's still the 2 there. So that's 3 over 4. Minus 3 over 4. Okay, bear with me there. Minus 3 over 4. And where we see, all right, let's see, that's a 3 there. Let's go, we need to just quickly wrap it up here. And that is supposed to be 3 into minus 3 over 4. All right, so what you'll then have is a 9 times 2, that's 18 over 4, minus 9 over 4. All right, so that gives us 9 over 4. So we then come and represent all these values here, and this has been shifted to the left, so your symmetry is over there, and let me just wrap it up. It passes through there, and the turning point is over there. That's how your graph is going to look like. All right, so we've shown the important features because this was, our other x-intercept, which was minus 3 over 2. Yes, minus 3 over 2 and 0. And that we said is minus 3 over, that's it. Okay, so I think we can wrap it up there. Minus 3 over 4. Okay, Katleho?
Okay, thank you,
Yeah.
Iti.
All right.
Thank you for that.
Great.
Thank you, Mindsetters. It was such a jam-packed show. As we know, time goes extremely fast when we're having fun. So I hope you guys had all the fun that you could have today with our functions. I hope you guys took extra notes and everything, and you're actually on the ball. Thank you again to Liberty for such an awesome show. Grade 12s are up next, so call all your grade 12 friends. If you still want to join us, please do. The more the merrier. Bye, guys.